Hi, this is Alex from devstories.eu. PyTorch Fundamentals, Episode 5 of 18. If you run a newly trained model on a large batch of test images without changing one specific setting, your application will eventually crash from an out-of-memory error. Even though you're just making predictions, the model is secretly hoarding memory to remember every mathematical operation it performs until the system dies. Controlling gradient tracking is how you prevent this. By default, PyTorch tensors are built to learn. If a tensor has its gradient requirement set to true, PyTorch tracks every operation performed on it. It builds a computation graph in the background, linking inputs, weights, and outputs, so it can calculate gradients later during backpropagation. This tracking engine is brilliant for training, but it requires a lot of overhead. When training is complete, your priorities change. Say you just finished training an image classifier and you need to run predictions on 1,000,000 new images. You do not need to update the model weights anymore. You only want the forward pass. If you leave the tracking machinery running, PyTorch builds a useless, massive computation graph for those 1,000,000 images, burning through your RAM and slowing down your compute cycles. To stop this, you have two primary tools. The first is a context manager called torch.nograd. You use this to wrap entire blocks of code. When you place your forward pass inside a nograd block, you are telling PyTorch to temporarily shut down the tracking engine. Any operations performed inside that block will not be recorded. Even if the input tensors are normally tracked, the outputs created inside the block will have their gradient requirements set to false. This is your tool for running evaluation, testing, or bulk predictions. It turns off the graph for everything inside its scope. The second tool is the detach method. While nograd handles blocks of code, detach handles individual tensors. Calling detach on a tensor returns a new tensor that shares the exact same underlying data as the original, but it is completely disconnected from the computation graph. It has no history. People often confuse when to use which. Use the torch.nograd context manager when you want to silence tracking for a sequence of operations, like moving from training to inference. Use the detach method when you are actively building a computation graph during training, but you need to pull one specific tensor out of that graph. A common use case for detach is when you need to pass a tensor to a different Python library like NumPy, which does not understand PyTorch computation graphs. You detach the tensor first, stripping away the tracking baggage, and then hand over the raw numbers. Disabling gradient tracking is also a core technique for freezing parameters. If you are fine-tuning a massive pre-trained model, you probably do not want to train the entire thing from scratch. You can loop through the base layers of the model and set their gradient requirements to false. PyTorch stops tracking them entirely. During the backward pass, those frozen layers will not calculate gradients and will not update, saving massive amounts of memory and dramatically speeding up your fine-tuning process. Gradient tracking is heavy industrial machinery designed strictly for learning. Whenever a tensor does not need to learn, shut the machinery off to reclaim your memory and speed. That's all for this one. Thanks for listening, and keep building.